Most students are taught that some integrals are just unsolvable. They will see the integral x to the power of x dx and assume there's no clean answer. But in 1697, Johann Bernoulli proved them wrong. This is the Sophomore's dream, and today I'm going to show you the elegant path to a solution. No heavy grinding, just pure mathematical strategy. The problem with x to the power of x is that the variable is in the base and the power. It's a moving target. Our first move is to rewrite it using our favorite constant, e. Why e? Because remember the identity. X is equal to e to the power of ln x. So we could transform our function x to the power of x as e to the power of ln x to the power of x, which equals to e to the power of x ln x. So now the variable is only in the exponent. We've turned a double variable problem into a standard exponential one. And now, the power series expansion. We can use the Taylor series for e to the power of u. This is like the cheat code for dealing with complex exponents. We know that e to the power of u by Taylor series is equal to summation from n equals to 0 to infinity of e to the power of n divided by n factorial. Plugging in our u equals to x ln x, we'll have x to the power of x equals to summation n equals to 0 to infinity of x ln x to the power of n divided by n factorial. So we can now move the integral symbol inside the sum. Our goal is no longer to solve one big integral, but to solve an infinite number of small ones. The core of our problem is now evaluating summation from the integral from 0 to 1 of x to the power of n times ln x to the power of n dx. This looks messy, but we can solve it instantly using a substitution, u equals to negative ln x. Why negative ln x? Well, because this transforms our integral into a gamma function structure. Without getting bogged down in the weeds, the result of this specific integral would be x to the power of n ln x to the power of n dx equals to negative 1 to the power of n times n factorial divided by x plus 1 to the power of n plus 1. So, notice how the n factorial appears. Now if we can put it all back together, our sum was summation n equals to 0 to infinity of 1 divided by n factorial times x ln x to the power of n. So we can rewrite this as summation of n equals to 0 to infinity 1 divided by n factorial times negative 1 to the power of n times n factorial divided by n plus 1 to the power of n plus 1. So here, the n factorial on top and bottom cancel out perfectly, which leaves us with summation n equals to 0 to infinity of negative 1 to the power of n divided by n plus 1 to the power of n plus 1. Or by shifting our index to start at 1, the final simplest form of the sophomore stream is going to be integral 0 to 1 x to the power of x dx is equal to summation n equals to 1 to infinity of -1 to the power of n minus 1 divided by n to the power of n, which looks like 1 minus 1 divided by 2 squared plus 1 divided by 3 cubed minus 1 divided by 4 to the power of 4. So this approximately will equal to 0.7834. It's a beautiful alternating series. So if you like this problem, subscribe and stay curious.